Hi, this is Dr. Emenacker. In this particular video, we're going to take two ideas that we've already been working with, one of those being limits, and the second one being difference quotients. And we're going to put these two ideas together to develop a very important concept in calculus. This is the idea of a derivative. Okay, so what is a derivative good for? Well, let's take a look at a situation. Let's say this gray graph here indicates, I don't know, sales, weight gain of cattle. It represents whatever, something or other in a business setting or otherwise where you want to understand how is it changing over time. It's very important to understand how things change over time. If automakers didn't understand how things changed over time, we'd still be driving Model Ts. Okay. Or somebody would drive a Model T with one additional item on it. Well, what winds up happening is clearly we're not driving Model Ts anymore, but things change, they improve. And what we need to be able to do is to track improvements, to track where things are going long term. This allows you to determine where a business is going, okay, so that you have some idea how to prepare for the future. Okay, so let's talk about change. Change is typically measured by a slope. If we look at this red line approximates the slope at a specific point. That point being right here, x, f of x. Okay, to get the slope of a line, we need 2 points. However, if we're going to be on this graph, there's only one location, one point we're actually interested in, and that's x, f of x. With just one point, you can't get a slope. Kind of leaves us with a problem. Well, the way this is addressed is from our x value down here on the x-axis, we're going to move over some amount. We're going to call it x plus h. Now, when we move over there, it gives us this second point up here on the graph. And if we come over to the vertical axis, we now have the function evaluated at this new x value, x plus h. So we have a second point. This second point is at x plus h, f at x plus h. H represents how far are we away from our original value that we're interested in. X is what we really want to understand. We want to understand what's going on at that location. Okay, that could be what's happening with sales in the month of July. Okay. Okay. Now the advantage to having 2 points is we can draw a line. We can draw this line here. It's a secant line. The line goes through 2 points on the graph. Okay. But the catch is it does not exactly have the slope at the one point we're interested in. It doesn't have the slope of that red line. It's pretty close, okay? But it's not the slope at that line. So what we can do is to say, well, gosh, I think I can improve on this a little bit. And the way you improve on it is by taking h and making it smaller. So, okay, the amount that I step away from my original point, this will be my new x plus h, is going to be this amount, which is then going to leave me with a y value over here like this. When I create this new point and I draw a secant line through those 2 points, notice that this orange line now has a slope, a tip, that is a lot closer to being that of the red line than did the green line that we were just working with here a minute ago. I'll put this green line back in. You can see that as we choose x values down here on the x-axis, that are closer to the point we're interested in, the slope of our secant line gets closer and closer and closer to being the slope of the tangent line. What we really want to do is we want to get the slope of the tangent line, but we cannot because it takes 2 points. Okay, so how do we handle this? Well, the way we're going to do this is we're going to let this distance between the two x values, okay, now I'm just looking at what's at the x-axis here. I'm going to let this distance, which is h, approach 0. Remember, with a limit, you can never actually get to that point, but you can get very, very close. So what this allows us to do is, with our choice of x, it allows us to move in closer and closer and closer and closer. And as we move in closer and closer in the x direction, our second point, which is on the graph, moves in closer and closer and closer to the first point, the point we're interested in. But because we've said h approaches 0, it never exactly becomes that first point. There's always some little distance between them. So for example, we can start out with h is 0.1. We can move and say, okay, we're going to just be 100th of a unit away from our original value. Well, we can get better than that. We can get 1,000th of a point away. We can then get a 10,000th of a point away. I think you can see the idea. The distance between our original value and our second point gets smaller and smaller. The distance gets smaller. To give you an example with real numbers, let's do something like this. Okay, let's see here. We've got a graph there. I'm going to pick my value here is x equals 1. Now at x equals 1, the y value is going to be whatever the function is evaluated at 1. I don't know what the function is for this graph. Might be part of a parabola. If I want the slope of the tangent line, remember that tangent line only touches at one point, that point being where x equals 1. What I can do is I can choose some other x value. For example, maybe I'll choose x equals 2. If I choose x equals 2, that means my step size is 1. The distance from 1 to 2 is a step of 1. Okay, well, I can get closer than that. I can let x equal 1.5. Well, if I let x equal 1.5, I've now moved here, and I have x equal to 1.5, and now the distance between these 2 points is 0.5. Continuing with this idea, I can choose x equal to 1.1, and you can see that's getting closer to 1. There, the step size is 0.1. If I choose x equal to my second x value, 1.01, now the step size is 0.01. You can see here that I'm just getting closer and closer and closer, choosing x values that are closer to 1, but never actually choosing 1 as my second point, because it's not a second point, it's the point we've already dealt with. As we allow these x values to draw closer together, the tangent line that we create gets very, very, very close to approximating the red line. Actually, it's not a tangent line we're creating. The secant line that we create gets very, very close to approximating this red tangent line. The whole idea of a derivative, okay, don't miss this. The whole idea of a derivative is letting that step size go to 0. Okay, so what we're going to do now is we're going to spell out the definition of a derivative. Now, basically, what the definition of a derivative is the slope, which is going to be equal to the derivative, and I'm going to use this notation f prime of x as the definition of a derivative is equal to, now here come the two ideas that we've already worked on. Save some space in front here. I'll come back and put something in there. With our quotient rule, we have 1 point, x plus a, the f of x plus h, and because we're doing a slope, you put the y value over its corresponding x value. Okay, so this comes from, let's move up here, the second point, the point in green. Okay, it's our second point. It's somewhat removed from our point of interest, x, f of x. Okay, but there we have that point. Now, as we compute a slope, we're going to subtract our point of interest. Well, the y value there is f of x, and the x value there is x. Okay, so there's the difference quotient thrown in. It's basically just a slope, no big surprise there. The second idea we've talked about here is we want h to get smaller. To show that we're going to let h get smaller, we're going to use the limit as h goes to 0. And as you can see here, here we have our limit as well as our difference quotient, the two ideas we've been working on becoming comfortable with up to this point. With this definition of a derivative, and this is really important, okay? It is very, 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 very important that you know this. Know this as in, this is an equation you've got to know. We're going to use it sufficient number of times that odds are you're going to memorize it whether you try to or not. Okay, so what do we do with this? Well, I'm going to work an example here, and this example is very similar to what's in the homework. In fact, it's very similar to what's in the homework in the first, what, 15, 16 questions. Okay, let's say we have something like this. We have something like y equals x squared. And you're asked to use the definition of a derivative to compute an equation for the slope anywhere along this graph. Now, if you'll recall, x squared is a parabola. If we draw a tangent line anywhere along here, the slope is going to be slightly different than it is at any other location on the graph. So we need an equation to describe the slope anywhere along the graph of the parabola. To get the equation, what we're going to do is we're going to use this definition of a derivative. Okay, so using the definition of a derivative, I'm going to put down at f prime of x. This f prime of x is the notation we're going to use to say, hey, this is a derivative. To say, hey, we use the limit as h goes to 0 of f of x plus h minus f of x over x plus h minus x. Now, something that will happen in every single case, in the denominator, you can see that you have x plus h minus x. It will always be the case that the x's subtract off, and in reality, the denominator simplifies to just be h. All right, so we have our definition of a derivative written down. Now, what I'm going to do is I'm going to put my y prime equals, and it's very, 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 very important that you continue to use this notation, the limit as h goes to 0. The denominator I'm going to simplify to be h, because x plus h minus x, the x subtract off. Let's take a look in the numerator. This notation here indicates that we're going to use our equation. The equation's in the upper left-hand corner. In this case, our equation is you take whatever is the variable and you square it, x squared. However, for this particular problem, it says x plus h. So I'm going to substitute x plus h in here minus the second term in the numerator says to copy down my original function, f of x. Well, that's just going to be x squared. Okay, at this point, it's algebra time. We're going to focus on what's going on in the fraction. So I'm going to leave this limit as h goes to 0 out front. Notice I cannot substitute 0 in for h at this point. Okay, if I do, I'll get a 0 in the denominator. You can't plug 0 in for h. But what I can do is in the numerator, I can expand this x plus h squared. This is going to give me x squared plus 2xh plus h squared. Be really careful. A lot of people see this x plus h squared and they want to write this as x squared plus h squared. That's not true. It is not true because x plus h squared really means x plus h times x plus h, and you have to FOIL it out. Okay, so that first term is actually x squared plus 2xh plus h squared. The second term is our minus x squared. There. Remember, we can't plug 0 in for h because it'd give us a 0 in the denominator. That's a problem. All right, so let's keep going with the algebra here. We have this limit as h goes to 0. We're going to have our h in the denominator. In the numerator, we have an x squared here minus an x squared there. Those will subtract off. Nothing else subtracts off, which means our numerator is going to continue to have 2xh plus h squared. This can be rewritten as the limit. Notice you got to keep bringing this limit along. You can't drop it anywhere along the way. In the numerator, both terms have an h. I can factor the h out, which is going to give us 2x plus h. Factoring this x out is actually, or h out, is actually very nice because now we have an h in the numerator that we can cancel with the h in the denominator. This allows for something really nice. What happens now is we have this limit as h goes to 0, and what we have is the 2x plus h. Hey, wait a minute, this looks like what we've seen back when we were working with limits earlier. Now we can substitute 0 in for h, and it leaves us with 2x. Remember on the left-hand side, we've been writing, or started by writing y prime or f prime of x. This tells us then that our derivative is 2x. If you'll recall, back at the start, I mentioned that for something like x squared, which is a parabola, okay, I'm looking back up in the upper left corner of the screen, I mentioned that the tangent line is going to have a different slope every place on the parabola. And what we actually need is an equation to compute what the slope is going to be anywhere on the parabola. At this point here, this is an equation for the slope. Now, really important, the slope will always tell us how something is changing. We'll see this in a little bit. Okay? Suppose you were asked the following. Compute the slope at x equals 4 when f of x is x squared. Notice the function we're working with is x squared, the one we just did. To get the slope, it's really easy. We just bring the equation down. It's in the blue box up there. It's 2 times whatever the x value is. And the x value we're interested in here is 4. So the slope is going to be 8. Okay, we can take this a step further. And when we take this a step further, this is exactly like the homework problems 17 through 22. Okay. Real fair question is, compute the equation of the tangent line when, let's say, x equals 3 and f of x is equal to x squared. Okay, this is very, very similar and in fact matches up with on page 144 in your book. It matches up exactly with the idea that's asked for questions 17 through 22. Okay, we're asked to get the equation of a tangent line of a function, in this case x squared, at a particular point. Now, to get the point, the x value is going to be 3. To get the y value, all you have to do is substitute it into our function. The y value is 9. So if we're asked what is the equation of the tangent line when x is 3, that means the y value has to be 9, and the function is f of x equals x squared, real straightforward. Remember, we're going to be using the equation y equals mx plus b. Okay, the first thing we need to compute here is the slope. Well, the slope is going to be not the x squared. Remember, oh yeah, up there at the top of the screen, the slope is the derivative, which is going to be 2 times my x value. In this case, the x value is 3, so the slope is going to be 6. Okay, so we have our slope. Now, the next thing we need to compute is b. For me, an easy way to compute b is instead of going back to the point slope form, to just take the point that I know is on the line, and notice we know that x equals 3 and y equals 9 is on this line. So I'm going to rewrite this as the y value is 9 is equal to the slope times the x value plus b. Okay, so this gives me 9 equals 18 plus b, which then gives me that b is equal to a negative 9. Just subtract 18 from each side. So I have my value for b. Up in part 1, I have my value for the slope, and I can write my equation. Y equals mx plus b becomes a slope of 6 plus a negative 9, so it's 6x minus 9. This is the equation of the tangent line at x equals 3. Let's do another one of these. Okay, I'm looking at question number 16 in the homework. So this is going to be on page 144. Number 16. I'm using this as another example of how do you compute the equation of a tangent line at a point? Okay, so if you take a look at number 16, well, I'll tell you what, let's not do number 16. Let's do number 19. Yeah, let's do number 19. If you look at number 19, you're given that f of x equals 2 over x. And one of the points you're asked to work with, not the only one, but one of the points is the location of, let's see, 1, 2. The first thing you want to do is make sure that this point really is on the graph or on the function. If I plug in the x value of 1, the y value really does work out to be 2 because I have 2 over 1. It's all good. Okay, so we're asked here to find the equation of the tangent line. To get the equation of the tangent line, we need a couple of things. First, we need the slope. Second, we need a value for b. Remember, when we're doing a line, it's going to be y equals mx plus b. Okay, so that's why we need a slope and we need a value for b. Okay, first, let's take a look at how are we going to get the slope. So assignment number 1 or project number 1 on this is we need to get the slope. The slope mathematically is indicated as the derivative of the function f prime of x equals. How am I going to do this? How am I going to get the derivative? Well, to get the derivative, I'm going to use that definition of a derivative. The limit is h goes to 0, f of x plus h minus f of x. And in the denominator, remember, it always simplifies to just be h. So I'm just going to run with that. I could have put x plus h minus x, but hey, that would have simplified to be h anyway. Now, remember, our function in this case is 2 over x. So as I go about computing the derivative, I'm going to have my limit as h goes to 0. In the denominator, I'm going to have h. Now, here comes the fun part on this one. This time, our function is 2 over x. Well, the notation indicates that I'm going to pick up the function, and where x is, I'm going to substitute in x plus h. Okay, so I have 2 over, and where the x goes, what I want to plug in is an x plus h. Minus the second notation here indicates that I just want to copy down the function. Well, that's 2 over x. Great. I'm sure you're all excited about this. We have a fraction minus a fraction over a fraction. Well, we're going to solve or work with this one step at a time. For right now, I'm just going to work with the numerator. So I'm going to keep my limit as h goes to 0. In the denominator, I've got this h. To combine the two fractions, the first thing I need to do is to get a common denominator. Okay, the first fraction in the denominator has a factor of x plus h. The second fraction has a factor of x. So I'm going to take the first fraction and I'm going to multiply it by whatever the denominator is in the first fraction. Then I'm going to take the second fraction and multiply it by whatever the denominator is in the first fraction. When I do this, my first fraction is going to have a denominator of x plus h times x. Numerator is going to be 2x minus. In the second fraction, the denominator is going to be the x plus h times x. But be careful, this time I got to take 2 times x plus h. In other words, I have to distribute. And I'm going to get 2x plus 2h. Okay, so there we've got that taken care of. We now have a common denominator. Still need to bring along this limit as h goes to 0. You've got to bring this along until you get that h canceled in the denominator and you can actually substitute 0 in for h. Okay, so what's going to wind up happening here is when I combine the two fractions, I'm going to have x plus h times x as my denominator. Now, in the numerator, I have 2x minus 2x. Those cancel. And I also have a minus 2h. Okay, well, at least it's not as complicated looking. Way back somewhere, probably about 7th grade or thereabouts, 8th grade, you may have learned that when you have a fraction divided by a fraction, you invert and multiply. What we actually have here is a fraction, the minus 2h over x plus h times x, divided by another fraction. And you may look at that and say, no, that's just h. Yeah, but we can rewrite this as x or h over 1, and now it's a fraction. Okay, so when we rewrite it like that, we're going to have the limit. Remember, we have to continue copying this. As h goes to 0, and we're going to have this minus 2h over x plus h times x times, now I'm going to take what's in the denominator and I'm going to invert it. When I invert that, we have a 2h in the numerator and we have an h in the denominator. These h's will now cancel. When they cancel, I'll move this up a bit, we now have a limit as h goes to 0 of negative 2 over, we have our x plus h times our x. At this point, we can plug the 0 in for h, and it's not going to be a problem. We're going to have the negative 2, then we're going to have x plus 0 times x, which is really going to give us a negative 2 over x squared. This is our derivative. So in this case, our slope, which is going to be our f prime of x, is the formula negative 2 over x squared. This, whoa, is what we're going to use. Let's go way back up here. It's what we're going to use up here. Oh, that's right. Remember, the first thing we were trying to do here was to determine the slope. Well, our slope is going to be defined by a negative 2 over x squared. So this is going to be a negative 2 over, what's our x value? It's 1 squared. So at this particular value of x, the slope is a negative 2. Well, that was a lot of work. It is a lot of work to compute these derivatives using this definition of a derivative. We're not done with this problem yet. Remember, we need the equation of the tangent line, y equals mx plus b. Okay, so let's move on down here a little bit. We're still working with y equals mx plus b, the equation of the tangent line. We've computed our slope. Our slope is a negative 2. We're working with the point 1, 2. Now what we need to do is we need to do the second part, which is compute b. Okay. To compute b, I'm going to use this y equals mx plus b. I know my y value is 2 equals. I know my slope is negative 2. The x value is 1 plus b. When I solve for b, b equals 4. Okay, so there's the second part. The first part was to compute the slope. The second part is to compute b. Okay, you want to be careful with these. You've got to compute both parts. Then we have to substitute in the slope, the original x value and y value, the original point that we're interested in working with, to compute b. And once we have all this done, now we can come back and we can say, okay, y is equal to our slope is negative 2x plus our b value is 4. This is our final solution. This is the equation of the tangent line at the point 1, 2, when f of x is equal to 2 over x. These tangent line equations are going to be very important. We're going to talk about these later, how you would actually use these in a business setting. Okay. Now, this took a ton of time to get through this. I understand that. This is just one homework problem. Okay. This is an example of how you would work number 17 through 22. Okay. Another important idea we need to look at in this particular video is when do these derivatives exist? They don't always exist. Remember, in order to get this derivative, we are using a limit. And we've seen situations in functions where limits do not exist. We are going to encounter a number of places where limits are undefined or where the derivative itself is undefined. And essentially what we're after is, where do the derivatives exist? There are three problem areas. Okay, you're going to be looking for these three problem areas every time you come across a problem. These are the places where the derivative does not exist. The first place where a derivative does not exist is a discontinuity. We've already worked with these. These are situations where you have a graph that might go like this, and there's a break in it, and it goes like that. That is a point where a derivative does not exist. A second point where a derivative does not exist is what is called a corner, or they're also referred to as a cusp. This is situations where the function is continuous, but it does something like that. Now, the reason a derivative does not exist here is there is not one tangent line. We could draw a line like that. That only touches the graph at one point. We could draw a line like that. That only touches the line at one point. We could draw a line like that. That only touches it at one point. And there are an infinite number of lines that we could draw like that. Okay, so three places where derivatives do not exist. One of them is where you have a discontinuity. The second is where you have a corner or a cusp. And the third location where you do not have a derivative is where you have a vertical tangent line. On a graph, this is going to look something like this. You have a graph. The graph comes along, and for just a moment, it goes vertical and then over. The tangent line is vertical at that location. Now, why do you not have a derivative there? Well, remember, on a vertical line, the slope does not exist. If the slope does not exist, you can't have a derivative because a derivative is a slope. A derivative talks about a slope. Okay. Okay, so there's a whole lot of information here. I would encourage you to go back through and practice these things. In particular, practice situations where you're given an equation. Well, let's try something like this. Let's say we have 3x squared plus 6x, and you're asked to compute the derivative. Let's run through this one. This is very similar to problems like number 11 and number 13 in your homework. Tell you what, let's add in plus 5. So it is very closely paralleling number 14 and number 15 specifically. To get the derivative, okay, be patient. This is going to take a little time. If you get lost, you can rewind or back up on the video. Okay, but you need to hang in there and follow this all the way through because first off, computing a derivative using the definition of the derivative is a real fair question on an upcoming quiz, and it will be question number 1 on test 2, worth about 10 points. That's a letter grade. Okay, we're using the definition of a derivative. That's this thing here in the blue box to compute a derivative. Okay, so how are we going to work this? Well, our first step is going to be we're going to do this limit as h goes to 0. And remember, in the denominator, we're going to have our h. Okay, so what else are we going to have? First off, we're going to have our 3 times x plus h squared plus 6 times x plus h plus 5. Where did that all come from? That came from taking the x plus h and substituting it into our original equation. That is not the entire numerator. That's just the first part. Remember, we still have this second part to contend with. Minus, be really careful to put this in brackets because the whole thing gets subtracted. 3x squared plus 6x plus 5. The whole thing gets subtracted there. Be careful. If you forget the brackets, you'll just have minus 3x squared. Then you'll be adding the 6x and adding the 5. And you don't want to add them. You want to subtract them. Okay, so where does this take us? This is going to be equal to, now I'm going to have to expand some stuff here. We're going to have our y prime equals, we're going to have this limit as h goes to 0. This is going to take a while. In the numerator, I'm only focusing right now on this first piece. So in the numerator, I'm going to have 3 times x plus h squared. Well, that's x squared plus 2xh plus h squared. We've already squared x plus h earlier. You've seen where the x squared plus 2xh plus h squared comes from. Plus, now what I'm going to focus on is the second term. This says we have to distribute 6. So it's going to be plus 6x plus 6h. There's the second term. The third term is just plus 5. So we have all of that from the first part. Now, I'm going to distribute the negative sign. I'm going to have a minus 3x squared, going to have a minus 6x, and a minus 5, distributing the negative over all 3 terms of my polynomial. Next step, equals the limit as h goes to 0. It's still all going to be over h. In the first term, I need to distribute the 3, which is going to give us 3x squared plus 6xh plus 3h squared. I took the 3 and multiplied it times each of those terms. Then, next to that, I still have my 6x plus 6h to add in. So I have plus 6x plus 6h plus 5. I really don't need the brackets at this point because I've distributed the subtraction. So I have a minus 3x squared minus 6x minus 5. At this point, I'm going to combine like terms. I have a 3x squared minus 3x squared, a plus 6x minus 6x, a plus 5 minus 5. Okay, when all that cancels out, I have a limit as h goes to 0. What's left in the numerator? A 6xh, a 3h squared. Let's see, I have a plus 6h. Everything else in the numerator has canceled out. Notice what is left in the numerator. Every term has a factor of h. So I can factor out an h, and I have this limit as h goes to 0. I'm going to have my h in the denominator. I'm going to have an h here times 6x plus 3h plus 6. At this point, I have an h in the numerator factored out that will cancel with the h in the denominator. This then allows me to rewrite this as the limit. As h goes to 0, you must continue to bring along this limit notation until you actually plug in 0 for h. I've not plugged in 0, so I have to continue to carry that. This is going to be the 6x plus 3h plus 6. Now, at this point, there are no h's in the denominator, so I can substitute in 0 for h. And notice when I substitute in the 0, I've dropped the limit. This then gives me now a simplified equation, 6x plus 6. This is the derivative. This isn't the whole problem, okay? This is my derivative. Can be written as f prime, can be written as y prime equals 6x plus 6. Okay, so that would be something like the first part of 17 through 22, where you first have to compute the equation of the slope. If I wanted to determine the tangent line, to y equals, let's see, I think it was 3x squared plus 6x plus 5 at, let's say, the point 0, 5. If I plug in a value of 0 for x, I get a y value of 5. I need two things. One, I need a slope. Two, I need to compute what's the b value. Well, I now have an equation for a slope. It's going to be 6 times my x value of interest is the x value from the point, plus 6. My slope is 6. To get the b value, I'm going to use my equation y equals mx plus b. Substituting in 5 for the y value, 6 for the slope, 0 for the x value, plus b. Remember, the x and the y values come from this point. When I solve for b, I get b equals 5. So the equation of the tangent line is going to be y equals a slope of 6 times x plus the b value is 5. This is very, very, very similar to, almost identical to 17 through 22. In 1 through 15, you're computing slopes. In every case, the slope is going to be computed using this difference quotient with the limit. I know these take time. You really need to practice these. You can go no further in calculus till you can do this. This is it. This is what the whole half of calculus is contingent on. Now, in the homework, if you take a look at stuff like 25 through 30, okay, you're going to be given um, you're going to be given some function. Let's say it does something like this. And you're going to be asked, where does this thing have derivatives? You're going to be asked to identify, list the values where it's not differentiable. Okay. And I'm going to throw something else in here. Tell you what I'm going to do here. Let's put something like that in. Now, where is it not differentiable? There are three situations where it's not differentiable. One is, where do you get a corner or a cusp? It's not differentiable at B. At A, it is perfectly fine. It's differentiable. It's continuous. There's no cusp. It's not vertical. It's fine. The next point where it is not differentiable is C, because it's a point of discontinuity. D is perfectly fine. Once again, it's smooth, it's continuous, it's not vertical. E is not differentiable because, once again, you have a point of discontinuity. The limit doesn't exist there. Lastly, at F, right here, it's not differentiable there because you have a vertical tangent line. If the tangent line is vertical, that means the slope is undefined. And if the slope doesn't exist, you don't have a derivative. Okay, so hopefully between the examples and working some problems very similar to the homework, that'll help you get through this. Be sure you practice these things. These things are so important.